Hello there, welcome to Seren's class, a channel where we make learning so easy and observable. We are excited to have you on the channel once again because it's been a while we studied in the classroom. You are welcome to the channel once again. Today we are going to talk about sets, and I am the humble facilitator, Sir Henry, also known as the children's uncle, and then today I will take you through sets. Now, a little bit of history about SET. SET is a topic that is treated in the senior high, but per the guidelines of the NACA, that is the new curriculum common core program, SETs have been introduced to JHS3 students, Basic 9. So in Basic 9, you'll be introduced to it. As you get to the senior high, you go in depth. So you have a fair knowledge of what SET means. So today I'm going to take you through SET. This will actually be part 1. There are more of it. So this will be part 1. Part 2 will also come the next time we meet in classroom. So get your pen, get your pencils, get your book, get your calculators, and let's start learning. It's a Harry's class, learning brought to your doorsteps. Let's get ready and go through sets. Okay, so sets. Now what are sets? One may ask. Sets are irrational numbers that cannot be reduced to whole numbers. Sets are irrational numbers that cannot be reduced to whole numbers. So if I have any number that cannot give me a whole number, then I'll call it a set. Basically, sets are written in a square root form, yes. And what also are irrational numbers? What makes a number irrational? In English, when you say something is irrational, meaning the number doesn't really make sense, something that does not really make sense, yes. So irrational numbers are numbers that cannot be written as common fractions. They cannot be written as vulgar or common fraction. Meaning such a number, I can't write it as a numerator over a denominator. Let's take a closer look at some examples. So we said basically the irrational numbers are mostly non-terminating and non-recurring decimals. Let's look at a number of them. So I'm going to write some numbers here. So if I have square root of 2, I ask you to find the value of square root of 2. It will be very difficult to do so, yes, because 2, as we see 2 here, is a prime number. And for prime numbers, it has only 2 factors, the number itself. So I want you to find a number that multiplies itself to give you 2. That would be very difficult, you tell me. Yeah. So I can't solve this unless I use a calculator. So if I have a calculator, I punch the roots on the calculator and then I give 2 in it. It's going to give me decimals 1.4142 with numbers that are not ending. So numbers that do not end are called non-terminating decimal. You can have a decimal where the number goes like that without ending. It changes as it moves. The number has no end. You can solve and solve and solve and solve and solve. So root 2 is a set because it will give me a number which I cannot write as a common fraction. If I also have pi, now we all know pi in decimal is 3.14157214, blah, with a lot of numbers. You can solve the whole day and then you will not finish. Basically, it is 22/7. Yes, so you solve 22/7 using the long division, and then you solve for days, for years, and then you still be working. The numbers are just moving on and on and on and on. Such numbers are irrational. I can't write them as a common fraction. Yes, and also such numbers do not end. We call them non-terminating decimals. Non-terminating. And as they go, the number gives you different numbers, different numbers. We call it non-recurring. When we say recurring, the number repeats itself. So if I have, let's say, 0.33333, that's 3/10. You see the number repeats like that. 0.33333 in that order. But so you can see 3 repeating itself. Yes. But here have different ones. So 3.141572154380. The number repeating itself. Then I have a non-recurring decimal. It's also non-terminating. So irrational numbers cannot be written as a fraction. That is why they are sets. If the number can be written as a common fraction, it is a rational number. Yes, so whole number, I know one does not repeat, one I have integers, -3, I write it as a fraction, I have -3/5, I have 1/2, all these things are rational, but we are concentrating on irrational numbers. So sets are irrational numbers. That cannot be reduced to a whole number. I believe you are getting it, yes. So that is set. So examples of set. Root of 2 is a set. Basically, sets are always written in a square root. Yes. So root of 2 is a set. Root of 3 is a set. Root of 5 is a set. Root of 7, root of 11, root of 13. So the root of prime numbers are sets. Yes, the root of prime numbers are sets. Yeah, or root of every prime number is a set. Please, yes. Yes, so the root of every prime number is a set. So far that number, you can't find two numbers to give you those numbers, then it is a set. Because looking at 5, I can't find two numbers that will multiply to give me 5. Because square root simply means that the number multiplies itself twice to give me that. So if I have a root of 4, I know it is 2 times 2, or 2 square will give me 4. If I have root of 16, I know 8 squared, or 4. I know 4 times 4 will give me 16, but here it is different. I can't find two numbers that will give me 3. I can't find two numbers that will give me 5. Yes, I can find 5 times 1. 5 times 1. I'll still get my 5 again. You see? But here the number multiplies itself. So it's not possible. 5 is not. 2 is not. 5, 7, 11, 13, they are all not possible. Basically, this is the idea of sets. Believe you are getting it. Yes, so sets are irrational numbers that cannot be reduced as common fraction. Or that cannot be, yes, cannot be written as common fraction, or they cannot be reduced to a whole number. Let's solve some examples. But before that, let's look at rules or properties. There are some rules or identities in sets. There are one or two that we should note before we can solve any set question. So let's look at that. Okay, so rules or identities of sets. Rules or identities of sets. The first one says that now if I have the root of the product of two numbers, the root of the product of two numbers. So let's say root of A times B. So they are all in the root of A times B. I can write them as individual sets. I can write them as root of A times root of B. That's the first rule or identity in sets. When you are multiplying sets, you can write them as individual sets. When you are writing sets, you can write them as individual sets in terms of multiplication. In terms of multiplication. So let's look at an example. So let's say I have root of 2 times 3. I know it's 6, yes. So I can write them separately as root of 2 times the root of 3. Get it? Yes, that's the first rule or identity in set. Product of two sets can be written individually or independently. The second property or identity says that if I have root of A all squared, root of A all squared, Now I have the square root of a squared. Squared in something means that the thing multiplies itself 2 times. So here it means root of a is multiplying itself 2 times. If I say 4 is a perfect square, I mean there's a number that multiplies its own self to give me 4. And that number is 2. 2 times itself 2 will give me 4. So here it means root a is multiplying itself twice. So I have root a times root a. Now this property can be used. I can multiply them to get this. And that will take me back to this. Now root of a times root of a is going to give me a. How come? I'm going to ask that. So let me explain. Now, note this. Every root is equal to half. Every root is equal to half in indices. So those that are the senior high. I know this lesson is not limited to those in JHS. Those in senior high is also an added advantage. If you are doing indices and logarithm in the senior high, one of the rules says that root of any number is half or is half. So here it means a half times a half. So a power half. It is a power. It's written as a power. Yes, indices. That's why I said indices. Power. So a power half times another a power half. Now the bases are the same. When they are multiplying, you add the powers. Half plus half will give me 1. Rules of indices. The product law. When two similar bases are multiplying, we add the powers. So here the power is half plus half. And half plus half will give me 1. You know, any base raised to the power 1 is the same base. That is why our answer is A. You get it? Good. So it means that root of a squared means that the answer is A. The square cancels the root to give you square roots. That's why we call it square roots. Square cancels roots. So if I have anything and I want to do away with the root, I introduce a square. So here, basically the square cancelling the roots, and it will be left with A. But this is the explanation behind it. It means they are multiplying themselves twice. And root means half, power half. So half plus half will give me 1. And that is why always square can cancel roots. If you get it. Yes. Okay. So, example. If I have the root of 3 all squared, what do you think the answer will be? The answer is 3. Square cancel root. Or root of 3 times root of 3. Root is half. So I can say 3 power half times another 3 power half. Since the bases are the same, I pick 1. Half plus half is 1. Any base raised to the power 1 is the same base. So the answer is I have a big root of A over B. So here is a division. The first one was a product. Here is a quotient, a division. Root of A over B. I can also write it independently like the first one. So I'm going to have root of A over a root of B. Yes, root of A over a root of B. Now, that is one identity or property. A root B plus of B, okay, plus of C root B. This one is an addition. A root B plus C root B. Addition of sets. Here, what do? You add, here we can call it quotient. You add the quotient or the ones in front of the sets, and since the one in the roots are the same, you just pick one. Here, you just pick one, just like indices. You pick what is outside and you add it, and then you pick a similar root. So I'm going to have bracket of A plus B. Since the roots are the same, I will pick one, root B. So I'll get A plus B root B. Sorry, A plus C. A plus C root B. A plus C root B. The last identity or the last property says that if I have A over root B, then it's equal to. So we call this a fractional set. This thing is called rationalization of set. We'll do that as a topic, but it's part of the property here. We'll treat that independently. but I thought it wise to add it to the rules. Yes, and it is part of the rules. A over square root of b. There's a fractional set, meaning a fraction with a set square root of b. What do? Here, you rationalize the set. It's an irrational number, but I can make it a rational number. That is the denominator. What do? Multiply this fraction by another fraction. So I'm going to rewrite the fraction again. A over root b. So I'm going to multiply it by another fraction. And what fraction is that? I pick the denominator and use it as my fraction. Let me come again. I'll pick the denominator and use it as my fraction. My set, root of b, will become my next fraction. So that root of b will be my numerator and denominator at the same time. So I'm going to get root of b over another root of b. So I'm going to multiply. We always assume there is a coefficient of 1. If I have a letter without a number, there's 1 in front. So a times 1, whatever is out multiplies what is also out. So a times 1 is a. So I have a, then the root b is joined. So a root b. Root b times root b. Root a times root a. What do you think? The answer will be b. And done. Very easy and simple. We'll treat this as a topic. This rationalization of set. We'll look at rationalization of set. I believe you follow me. If you have any question, don't hesitate. You leave it in the comment section box. I'll give you much explanation. I'll also leave my WhatsApp number. Maybe you want further explanation. I will be delighted to assist you. Now let's solve some examples, and that will be the last section of today's lesson. Let's solve some word examples. We are going to look at how to simplify sets. So simplifying sets. Simplifying sets. So some sets can be simplified. Yes, though we can't solve them, we can only use calculator, but some sets can be simplified. But sets like root of 2, root of 3, root of 5, root of 7, root of 11, root of 13, for such numbers, there's nothing you can do about them. Such numbers are already simplified. They are in a form where you can't do anything about them. So basically, when we say something is simplified, it means nothing can be done about it. For example, if I have 3 over 5, I believe nothing can be done about this. I can only leave it in decimal. But what if I've not been asked to leave it in decimal? But if I have 4 over 10, I can do something about it. I can use 2 to reduce it. 2 goes into 4, 2 goes into 10, 5. It has been simplified. Yes. So some sets can be simplified. Some sets can be simplified. Let's look at how we can simplify sets. Okay, now note the following. Now, let me also make this statement. Perfect squares are different from sets. Perfect squares are different from sets. But we use them in sets. We use them. But they are different. Yet they are not similar. If I have root of 4, root of 16, root of 9, root of 25, root of 64, root of 30, all these things are perfect square. Root of them gives me a whole number. So these are not sets. They are rather rational numbers because their answers are whole numbers. Here, I want an answer that is not a whole number. It is a non-recurring decimal or a non-terminating decimal set. But here, we'll use perfect squares in our solution. Yes. So note the following. If I have square root of 24, I can simplify it. Yes, of course. How do I do it? Here's the clue. We have to find product in multiplication. We have to find the product of a perfect square and a whole number. That will give us the number in the roots. Let me reframe the statement again. We have to find the product, meaning we have to multiply two numbers. And in multiplying those two numbers, we need one perfect square. Perfect square, that is one perfect square and one whole number that will multiply to give you what is in the root. So let's mention some perfect squares. So 4, but 2 will give me 4. 9, 3 will give me 9. 16, 4 will give me 16. 25, 5 will give me 25. 36, 6 will give me 36. 49, 64, 49, 64, 91, 100, 121, 144. All these things are perfect squares. All these things, or all these numbers are perfect squares. I'll leave some also on the screen so that we can, yes, all these numbers are perfect squares. So I want two numbers that will multiply to give me this. One of the numbers should be a perfect square. So what do you think? 4 times 6, 24. Yes. Let's check those two now if there is a perfect square. 4 is a perfect square because 2 will give me 4. 6 is a whole number. That is great. So I can write this as square root of 4 times 6. Now what did you say about multiplying two numbers under one root? That's why the roots are important. We can separate them. So we can separate this one. We are going to have root of 4 times root of 6. Root of 4 means I want a number that multiplies itself to give me 4. And that is 2 times 6. Here I can't do anything about the root 6. There's nothing that can be done here. Now there's 1 assumed to be here, coefficient. So 2 times 1 is 2, then root 6. And you are done. You can simplify some sets. So we'll be able to simplify this. Also, we can also simplify this one. What do you think? 9 times 2. 9 is a perfect square. Root of 9. Okay, so I write all of them under one root. Root 9 times 2. Separately as root 9 times root 2. Root of 9 is 3. Now we assume there's a 1 here. So 3, 1, 3, root 2. We can simplify some sets. So this is what we're doing. We'll be solving some questions under this. Believe you're enjoying the lesson. Good. So let's work some examples. Alright, so let's try and answer some few questions. Simplify the following sets. A, root of 8, B, root of 27, C, root of 128, and D, root of 200. So let's take number 1. Yes, so just like what we did earlier on, that is simplifying sets. So we find two numbers that multiply to give us with 8. 4 times 2, and 4 is a perfect square. 4 times 2. The first identity or property or rule, you can write them individually when you are multiplying them under one root. So the root of 4 times root of 2. Root of 4 is 2 times root of 2. We assume there's a 1 here. So 2, 1. What is out multiplies what is out. So 2, 1, 2, root 2. The first one, I have 2 root 2 as my answer. 2 root 2 as my answer. So let's move on to B. Root of 27. So here we find two numbers that will multiply to give us 27, where one should be a perfect square. 9 times 3. Yes, 9 times 3, and 9 is a perfect square. So 9 will give me 2. I write them as individual sets. It's 9 times root 3. Root of 9 means there's a number that multiplies itself twice to give me 9. And that is 3 times root 3. We assume there's a 1 here, but mostly we don't write it. The same we don't write 1 here, but I know there's 1 in front. So 3, 1 is 3 root 3. C, 128. Two numbers that multiply give us 128, and one should be a perfect square. 64 times 2. 2, 4, 8, and 2, 8, and 2, 6, 12, 128. So I have root of 64 times root of 2. Root of 64 is 8, because 8 is 64. So we assume there's a 1 here. So 8, 1, 8, root 2. I'll reserve the D as an assignment, and you can leave the answer in the comment section box. You can also send it to me on my WhatsApp line that I'll be placing on the screen very soon. So let's move on to 2. Simplify root of 8 times root of 5. And when we're going through the identities of property, we said that if I have two different roots, I can multiply them. The same way I can separate them and write them individually. So here, I wrote it this way. So this can also be written this way. The reciprocal of this is that. The reciprocal of this is that. The reciprocal of this is that. So I can have root of 8 times root of 5 is equal to root of 8 times 5. And 8, 5 is 40. That is not all. Can you simplify? Yes. Look for two numbers that will multiply to give you 40. 4 times 10. 4 times 10. And 4 is a perfect square. So I'm going to say 4 times 10. I have root 4 times root 10. Root of 4 is 2 times root 10. There's a 1 here, we assume 2, 1, 2. So the answer is 2 root 10. Following, let's go to the third one. Fast forward. So we have a root 5 squared. What did we say about multiplying the same root squared? Meaning the square cancels the roots. But here, don't just cancel straight, show working. So this is what we do. Root of 5 times root of 5. But they multiply themselves twice, and the answer gives you 5. But this is 5 and half, 5 and half. That's 5 power half, 5 power half. Half will give you 1. Any base raised to the power 1 is the same base. B. Root of 3 cubed. The same way square means they're multiplying twice. Cube also means they're multiplying 3 times. So here, root 3 can multiply root 3 and multiply it by the root 3. Now root 3 times root 3. Root 5 times root 5 is 5. So basically root 3 times root 3 is 3. In other words, 3 is 9. Root of 9 is 3. 5 is 25. Root of 25 is 5. You get that idea? Good. So here is 3 times root 3. We assume there's a 1. So 3 root 3. Very easy. Now, 4. Root 2 plus 3 root 3 plus 4 root 2 minus 2 root 3. This one is an addition and subtraction. It just came through, but we'll solve more of them the next time we meet in part 2. So here, we said you can add two sets when the roots are the same. So here, I have 3 root 3 and I have 2 root 3. So because of this root 3, I can solve this operation and that operation. So first, let's group like them and let's look at the ones with similar roots. They will come to one side. So the first one is root 2. So my root 2 will come, and I'll go through to see if I'll see a root 2 again. I have plus 4 root 2. So plus 4 root 2. I'm done with the root 2's. Now I go to root 3. So I have plus 3 root 3. And then I have minus 2 root 3. So now I can work them out because the roots are the same. Now we assume there's a 1, as I always say. So 1 plus 4 will give me 5. Since the roots are the same, we just pick one of them. We don't write the 2, we just pick one of them. Plus. Okay, so let's show working for. So here there's a 1 here. So 1 plus 4. Since they are the same, we pick 1 plus. So 3 minus 2. Since they are also the same, we pick 1. So 1 plus 4 will be 5. So 1 plus 4 will give you 5. I'll pick one of the roots, 2. 3 minus 2 is 1. But here we don't write the 1. So I just write my roots. Okay. Yeah. Last one. 3 root 500 minus 2 root 125. So here we are going to simplify the 2 roots. So I have 3. Now 2 numbers that multiplies into 500. 100 times 5. 2 numbers that multiplies give me 125. 25 times 5. So I can write this in a different way as root of 100 times root of 5. And root of 25 times root of 5. So 30 times root 5 minus 10 times root 5. So we group those that are here one side, and because they are subtracting. Addition and subtraction, when they are the same, you pick one. So we have 30 minus 10. Since they are the same, we pick just one of it. Now 30 times 10, 30 minus 10 is 20 root 5. And you are good to go. So this is something small on sets. This part 1, we are not done. Part 2 will also come shortly. We'll talk more of the addition and subtraction, and then how to rationalize set and approximating set. This is where we'll end for today's lesson. Thank you for having me. I am the children's uncle, St. Henry, your humble facilitator. Thank you for watching us, and God bless you. Keep subscribing and supporting us. If you have any questions, leave it in the comment section. Also give a number where you can send your concerns to. God bless you. Goodbye.